Okay, so those that we just covered were the main silicate non-ferromagnesian subgroups. Now we're jumping into looking at the silicate ferromagnesian subgroups. The ferromagnesian silicates tend to again be heavier in weight as well as darker in color than the non-ferromagnesian minerals, and this is due to the iron content for the most part. Okay, the first subgroup of ferromagnesian silicates is going to be the olivine group. This is a family of high-temperature silicate minerals. They are black to olive green in color and have a glassy to resinous luster. And they also have conchoidal or irregular fracture. Rather than developing large crystals, olivine typically develops as small rounded crystals that gives the olivine-rich rocks kind of like that green look, and it also gives them that granular appearance. So this is a common mineral in basalt, which is one of the most common igneous rocks, especially at mid-ocean ridges, which, as you know by now, based on plate tectonics lecture that we have, is the most common igneous rock in the ocean overall. Basalt is. Okay, so they're also common in peridotite, which is an intrusive igneous rock, and it is kind of the corresponding intrusive igneous rock from basalt. And we will look at all of this in lab next week when we cover chapter 4 on igneous rocks. Okay. Overall, olivine minerals are thought to constitute up to 50% of Earth's mantle, which is a very large amount. Again, this is the mantle, not the crust, okay? Distinctions. We have pyroxenes. These are pyroxene samples, which is another ferromagnesian subgroup of the silicate minerals. As you can see, they're typically black to dark green-black, kind of. They tend to have two-directional cleavage at 90-degree angles and be fairly hard, so they're about a hardness of 5.5 in mole scale. They also form a large portion of basaltic rocks. Another subgroup of ferromagnesian silicates are the amphiboles. Typically, they are black in color, ranging to kind of greenish, gray, or even dark brown at times. A hornblende is one of the end members of this amphibole subgroup, and it is the most common amphibole overall. It tends to be black, and it has two-directional cleavage at 60 or 120 degrees, as you're seeing there on the image on the left. It forms as elongate crystals that appear kind of splintery, and we'll see that in lab, so you get an idea of how that is. They're quite common in intrusive igneous rocks, which form the dark color content of many of them in a majority. So usually things such as granite or even diorite tend to have very little pyroxene and olivine crystals as the dark colored or ferromagnesian minerals that form the dark part of them. They tend to instead have a lot of amphiboles. Okay, so biotite is a dark iron-rich member of the mica family. So as you saw, or as you're seeing right there in the slide, it looks a lot like muscovite, which was the non-ferromagnesian end member that we had seen of the mica family. Like other micas, it also possesses a sheet structure that gives one-directional excellent cleavage. It also has a shiny black appearance that helps distinguish it from the other dark ferromagnesian minerals, because it does kind of shine a lot. And again, that we will see in chapter 8 when we look at metamorphic rocks a lot. It is also common in intrusive igneous rocks, not quite as much as amphiboles, but still quite common, and it gives them kind of a shinier tint every now and then. Lastly, garnets. So garnets are similar to olivine in their chemical structure, in their silicate structure, which means that they only have a single silicon-oxygen tetrahedron that is linked by metallic ions to the rest. It has a glassy luster, which lacks cleavage, or sorry, not which lacks cleavage, but rather it itself lacks cleavage, and it exhibits conchoidal fracture. It is most often found as red, purple, brown kind of, and that is one of the end members of garnet. Oh, but some varieties of it are also green. So its crystal habit is dodecahedral, so if let to grow without interruption, it will form as if resembling spheres with edges. So if it gets weathered, it typically appears as spheres. Garnet is also common in metamorphic minerals, meaning it forms as a consequence to metamorphism many times. Also, I'd like to correct something I said earlier in the previous, short video. I said that the end members of olivine were grossular and almandine. Those are the end members for garnet. Sorry, I got a little bit confused while in my own thoughts. The end member of olivine, I believe, are forsterite and phalite. But again, almandine and grossular are the end members for garnet. Almandine being the red, purple, brown one, and then grossular being the green one, which is less common. Okay, so after having looked at the different subgroups of silicates, again, those that were either non-ferromagnesian or ferromagnesian, this is a breakdown of the concentrations of those subgroups, along with the remaining groups in the crust. And remember that the silicate group itself already makes up 92% of the minerals in the crust. So as you can see, feldspars make a huge majority of all of the minerals in the crust with 51%. Then quartz is the next one with 12%. Pyroxenes go next with 11%. Amphiboles, mica family minerals, and clay minerals each with 5%. Other silicates, so again, that would be things like olivine, garnet, and whatever other ones I forgot to mention, with 3%. And finally, 8% of the crust minerals are of different groups, not having the silicon tetrahedron or silicon oxygen tetrahedron arrangement. So in the next slide, we will touch shortly on each of these non-silicate groups. Okay, so although non-silicate minerals only make up 8% of the crust, many of them, such as gypsum, calcite, and halite, occur as constituents of sedimentary rocks. And many other non-silicates are also economically important. So non-silicate minerals are usually divided based on the negatively charged ion or complex ion that the members have in common. For example, the oxides contain negative oxygen ions, so O2 negative, kind of, which bond to one or more kinds of positive ions. The most common non-silicate group are the carbonates, then halides and sulfates. Okay? Figure 3.3 in your book, which I believe is this one that I have in the slide, it shows all of the non-silicate groups with their specific key ions. So I won't go into detail on them, but I will point out the main minerals that we'll see in lab, at least, from these groups. And I encourage you to go ahead and look at this figure a little bit further on your own. So calcite is a mineral labeled A here in this image. It is part of the carbonate group. It has 3-directional cleavage at 60 and 120 degrees. It fizzes or effervesces with in contact with hydrochloric acid or HCl when it's exposed to it. And it is a main material or cement that many of the sedimentary rocks have. Halite, which, as you know already, is salt, or let's see, it's a halide. Where is it? Oh, right here. It's labeled C here in the image. So right here, it is a halide. It has 3-directional cleavage at 90 degrees. So you can see the difference in the different cleavage types between calcite and halite, for example. Gypsum, which is a sulfate, here labeled as I, has one directional cleavage. It is very soft and fibrous at times, and it is used in drywall a lot due to its properties. It can grow in and it can grow in very large crystals if allowed to. So in fact, the image at the beginning of this lecture is from a cave in Mexico with giant gypsum crystals. So check it out. In fact, I'm going to do it right now for you. So those are gigantic gypsum crystals that grew in this cavern in Mexico. And I believe that people who are going to study those gypsum crystals can only stay so long in the cavern without, being asphyxiated with the different fumes that are there within. Even with the suits that they're wearing, they can only stay, I think it's 10 minutes or so. So that's pretty amazing. Okay. So again, there are many, many, many different kinds of minerals that do not belong to the silicate group. And I encourage you to go ahead and read on this table or figure 3.3 later on your own. Or if you want, you can pause this video to check the rest of the minerals of these subgroups. Some of them we will look at in lab, such as galena, chalcopyrite, magnetite, fluorite. I can even show you a sample of dolomite. So we'll see a few of these in lab. So I encourage you to go ahead and pause the video, check out some of the different ionic bonds that they form and some of the different uses, especially that they have. Okay, so this is kind of like the wrapping up of this chapter. It wasn't as long as I was kind of expecting it to be, which is great. But most of the minerals in our planet fall under the non-renewable resources, so meaning they will not regenerate as quickly as we are extracting them and using them. Today, most products, as you should know, contain materials that are obtained from minerals. So the figure in the last slide lists some of the uses from these minerals, so definitely check it out if you're more curious about it. The USGS has very good resources for you guys to look at the different uses, for example, and I can post them later if you're curious. Okay, a few definitions. An ore deposit, or ore deposits themselves, are commonly named deposits where mining of a mineral resource occurs. Typically, we think of ores as gold and silver, for example, but ore refers to some non-metallic minerals as well. The mining for ores changes depending on the need for the resources that is being mined. It depends on the demand based on economic values for society, typically. So sometimes in history, they're more valuable, and some societies also make it more valuable. In order to have economic value, an ore deposit must be highly concentrated. For example, copper makes up 0.0068 of the crust, but for a copper ore deposit to be mined, the concentrations must be of 0.68%. So that means it has to be 100 times greater than the average amount of copper on the earth. Another example is aluminum, which can be mined as long as there are 3 to 4% of the specific of it in the specific concentration of rock that you're looking at. But as we saw earlier, aluminum is one of the elements that are most common in the crust, and it makes up 8% of the crust. So in truth, you only need so little of it in comparison to how much there is in the crust. So there are different regulations for the extraction of the different minerals based on demand, availability, and the methods that are used, etc. Something else to keep in mind is that many ore deposits contain more than one single mineral that is being mined. Sometimes only one or two of the minerals being mined has a good market value, which makes it hard to justify continuous mining. But the other minerals are good to mine at the moment. For example, the Bingham Canyon mine just outside of Salt Lake City produces nearly 25% of the refined copper in the US. But in addition to producing 300,000 metric tons of copper, it also produces about 400,000 ounces of gold, 4 million ounces of silver, and 25 million pounds of molybdenum. As geologists, we have now found a correlation between rock type and specific mineral concentrations. but also these are related to the processes that are involved in the rock cycle, such as weathering and erosion, metamorphism, fracturing, melting, etc. All right, so with that, we finished chapter 3. I hope this was a useful video for this chapter's material and that things were clear enough. If they weren't, please make sure to tell me and ask me any specifics or go back to the video, the slides, and or your textbook.